All right, this is the second part of section 8.2, operations on matrices, and we're going to go ahead and go into matrix multiplication. This is not the same as a scalar multiplication, which is basically just a number times the entire matrix or matrices. This is a matrix times another matrix. Okay, so here is a little bit of background information before we start an example. If we have these two matrices, okay, where A is an m by n matrix and B is a n by p matrix, then the product, if we multiply these two, is going to be m by p. In other words, we're kind of keeping the outer dimensions, if that makes any sense, to give us our products, okay? Couple things about this. The inner dimensions, so this dimension n and this dimension n have to be the same for this to work. If we multiply this, we're going to get this brand new matrix. We're going to call it with entries of C, where the entries are basically the row of one times the column of the other. And I'm going to show you how that works just a bit. Okay, it's important to note that we do have to have these inner dimensions to be the same. If they're not the same, then it's not going to work. Okay, so these two are equal. The column of this guy is the same as the row of this guy. And the ending result, the product, will be the dimension of the rows of A and by the columns of B. Okay, so M by P. For multiplication, here's a big hint. Always think row by column. Okay, so here we go. Here we're going to do a simple example and show how this kind of works. Okay, if we are multiplying A times B, okay, the first thing I'm going to do is I'm going to go ahead and write that out for us. So AB is going to be all of this. So negative 1, 4, 5, that's the first column. 3, negative 2, 0, times my B column. So negative 3, negative 4, 2, and 1. And you'll notice that the dimensions certainly are different. Okay, we have this guy is 3 by 2, so 3 by 2, and this one is 2 by 3. But you'll notice that the inner dimensions are in fact the same. So we are allowed to do this multiplication here. Okay, so let's go ahead and begin. When we multiply matrices, we are looking at for the first entry. Okay, so for the entry that goes right here, row 1, column 1, we're going to be multiplying this row by this column. And it goes entry by entry. So you're thinking negative 1 times negative 3 plus 3 times negative 4. And this is going to give me my first entry for row 1, column 1. Okay, so let's go ahead and do that for the rest of them, and then we'll move on from there. The next one's going to be, so this is, again, this is my A11, I guess you could think of it that way, entry. Okay, so let's look at the second piece right here. So this would be row 1, column 2. Well, that would be row 1. So now we're still looking at row 1, but now we're looking at column 2. So we do the same thing, negative 1 times 2, okay, plus 3 times 1. And it's kind of hard to see, but okay. And now we're going to look at the next one. So now we're going to be looking at the second row. So second row, first column. So I'm going to switch colors here. So second row, first column. So that's going to be 4 times negative 3 plus negative 2 times negative 4. When you get really good at these, you can do some of these in your head, okay? Second row, second column. So now we're looking at Again, second row, second column. So 4 times 2 plus -2 times 1. Okay? And last but not least, we have our third column, sorry, third row, column 1. So 5 times -3. Well, I'm sorry, that's the one that was, I remember that ink was giving out. So 5 times -3 plus 0 times -4. And that's this entry. Remember, each of these is an entry. Last one here, so it's going to be row 3. So again, we have, let me find a different color here. I'm out of colors. Let's use brown. So row 3, column 2. So row 3, column 2, we have 5 times 2 plus 0 times 1. Okay, and this is basically going to be our product. We're just going to simplify this because, well, that looks kind of weird, right? So from here, I'm going to go ahead and put my final answer. We have -1 times -3. Well, that's just going to give us +3, right? And then 3 times -4. So 3 times -4 is -12. -12, okay? And I'm just writing them kind of small so we can just keep track of what's going on here. 3 and -12 is going to give us -9. Yeah, that's a -9. I messed up the first time, so the -9. And then we're looking at the second place here. So we have 4 times -3. Again, that's -12. So I'm going to put it really tiny right here, -12. -2 times -4 is 8. So -12 plus 8 is -4. Okay. 5 times -3 is -15. 0 times this is just 0. So I have -15 in that third spot here, row 1, column 1. Sorry, row 3, column 1. Now we're going to look at this side over here. So we have -1 times 2 is -2. 3 times 1 is 3. -2 plus 3 is 1. 4 times 2 is 8. -2 times 1 is -2. 8 plus 2 is 6. Okay. And last but not least, 5 times 2 is 10. 0 times 1 is 0. So this last entry here is 10. So this would be our product of these two matrices. And we're going to check one more thing just so we can kind of see if this worked out. Remember from the way top up here, it said that if we're multiplying these two, the dimensions should be the outer dimension times the outer dimension. So m by p should be our resulting answer. So that means here, okay, the outer dimensions that we had were 3, 3. So, oh, I think I might have messed up here, guys. Oh, my bad. This is a 2. This should be a 2. 2 rows, 2 columns. See how easy it is to mess up? So anyway, we have a 3 by 2. This should be, AB should be a 3 by 2 matrix. So let's check. We have row 1, row 2, row 3. So for sure, we do have that 3 to begin with. Column 1, column 2. So we're good to go. Okay. And that's matrix multiplication. As you can see, it's very easy to make a mistake. So you do have to go a little bit slow maybe so you don't make a mistake like I almost did right now. Okay. We do row by column. I would recommend maybe doing this part first. I didn't do it till the end because I kind of wanted to show you, how this all came together. But I would recommend get this part up here first, so we can see what are the dimensions of my new matrix at the end. Okay, let's go ahead and try a couple more just so we can get the practice. So let's go to the next page. We have multiply this guy now. Okay, so the first thing I'm going to do here is I'm going to get the dimensions again. So we have 3 rows, so we have a 3 by 3 columns. So 3 by 3. This one is also 3 rows, but it's 1 column. So we want to check to first see if these two are the same, and they are. So that means that we can multiply this out. Okay? Remember, these two inner dimensions, these two have to be the same. Otherwise, this won't work. Okay? So that means that my resulting, my product of this is going to be equal to this outer one. So 3 by 1. So 3 by 1. That's what our final matrix should look like, okay? So let's go ahead and go right into it. Let's multiply this out. If we do for the first entry, we know it's going to be a 3 by 1. Okay, so I'm just going to make it kind of big so we can see. I'm going to go ahead and do my first row. So this row times this column. Okay, row 1 times column 1 is going to give me that first position of row 1, column 1. So that's going to be 6 times, so 6 times 1 plus 2 times 2 plus the third part, 0 times -3. That's all one entry, okay? Let's move on to the next entry. We have our second row here. So second row, but it's still column 1, okay? So 3 times 2 plus -1 times, oh, did I mess up? Oh, you see what I mean? 3 times 1, that should be a 1. Just full of mistakes today, guys. So 3 times 1, -1 times 2, okay, 2 times -3, okay? And last but not least, we're going to look at that third row. So now we have row 3, again, times our column 1. So that's going to be this place right here, row 3, column 1. So we have 1 times 1. I think my fingers are just, they're covering it when I do this. 4 times 2, so plus 4 times 2, plus 6 times -3. And this should give us our 3 by 1. So we see 3 rows, 1 column. Remember that this is just a number, this is a number, and this is a number. So let's go ahead and simplify this now. We have 6 times 1 is going to give us a 6 plus 4 plus 0. So 6 plus 4 plus 0 is 10. Okay. This one's going to give us 3, -2, and -6. So 3 and -3 minus 2 is 1. 1 minus 6 is -5. And last but not least, we have a 1, 8, -18. So 1 plus 8 is 9. 9 minus 18 is -9. So this should be our answer. And it looks like we are good to go. Our dimensions for this one are 3 rows by 1 column, which is exactly what I had over here. So we are good to go. Okay. By the way, this part right here, if you want to do a new matrix and do 6 plus 4 plus 0, 3 plus -2 plus -6, and so forth, you are welcome to. I'm just kind of skipping a few steps because it is a lot of work. That's the thing with matrices. They're not that bad. It's just a lot of writing. So we kind of, if we can take a shortcut, we might do it here and there. Okay, but it's up to you. Last example here on this page, on the page, not the notes quite yet. We have example number 8. And I already wrote here on the side that this is not defined. Okay, so let's see why this is not defined. We have for the first matrix here, we have 3 rows, so 3 by 2 columns. Okay, these are the dimensions. And then for this one, we also have 3 rows by 1, 2, 3, 4 columns. So what's the problem? They both start with a 3, right? Well, the problem is that these two are the ones that are supposed to be matching. Our columns for this one have to match the rows for this one, and they're not equal, okay? So because they're not equal, that means that this is not going to be defined. We cannot do this multiplication. And if you think about it, the reason these have to be equal is because this is a row, I'm sorry, this is a column and this is a row. When we multiply, we do row by column. So if we don't have the same number of elements in the row as the column on the other side, it's just not going to work out. Think of it. -2 times -2 plus 1 times 0 plus, oh, missing a term. So this 2 has nobody to pair up with. Okay, so that's why this is not going to work. So that's it for that one. Nice and easy. Next one. We're almost done. Almost done, guys. Hang in there. So this next page is a lot of copying, unfortunately. Here we have some more once this thing stops moving around. We have some more properties, just like we had with the addition of matrix multiplication. Okay, and basically it's something similar. Um, if C is a scalar, okay, remember a scalar is just a number that's being multiplied by the matrix. Okay, then some of these properties are going to apply. If we're multiplying three matrices like so, and two have a parentheses, we can move the parentheses around. This is the associative property. The left distributive property means that from the left side, we can distribute this A to get, two products, A, B, and AC. On the right, it's the same thing, but now we're going from the right, okay? And then we have the associative property of scalar multiplication, which says if I multiply these two and then I have a constant on the outside, or I shouldn't say constant, a scalar, it's the same as if I multiplied it, um, with the parentheses on the outside, or if I multiplied it first and then times the A, it's still going to be the same thing, okay? Another important thing on this page is the identity matrix, and this is a really big one that you do need to have absolutely for sure, because we're going to see it in the next section here of 8.3, I believe. We have this special matrix that's called the identity matrix, and it's kind of like a one. Think of it like one times anything is itself, right? It kind of works that way. It is a square matrix because the dimensions are the same n by n, and it has a bunch of ones that are on the diagonal. So you'll have like a diagonal of ones all the way down this way, okay? And the rest of them are just zeros. This is called the identity matrix of dimension n, and it's denoted by this I or I subscript n. So both of these mean identity. Okay, this means the identity matrix. Okay, this or this. And I did mention right now this is also called a square matrix since it's n by n. Remember, a square matrix is going to have the same dimensions, so this one has n by n elements. Okay, so let's go ahead and just kind of use this property so you can see how it works. So we will be using it with inverses in particular in the next subunit. For example, 9, we're going to use the identity matrix and say that if A is equal to this, A times the identity is still going to give me A, okay? First of all, we should take note that A is a 2 by 2 matrix, which means that our identity matrix, I sub n, in this case, is also going to be a 2 by 2 matrix. Remember that these types of matrices have ones along the diagonal, which means we have a 1 here, 0 everywhere else, 1 here. So we're going to go ahead and do this multiplication now. A is going to be this over here, so -3 times 4. Oh, sorry, not times 4, -3 and 4, and then 2 and 5. We're just copying the matrix. This is A, okay? And then our identity matrix is over here, so we're going to multiply times 1, 0, 0, 1. And we're going to see if this, in fact, gives us A. That's what we're trying to prove. So let's go ahead and do our operations for the first entry. So for row 1, column 1, we're going to do row 1, column 1. So that would be -3 times 1 plus 2 times 0, okay? For the second, I'll get a different color here. For the second entry here, we're going to have row 2, column 1. So 4 times 1 plus 5 times 0, okay? Moving on to the first row, second column. So now we're doing row 1, column 2, okay? So -3 times 0 plus 2 times 1. And then last but not least, we have row 2, column 2. So row 2, column 2, which will be 4 times 0, and then plus 5 times 1. And we're going to see if this in fact gives us the exact same thing as A. So what does this equal to this? Well, let's see. This is going to be negative 3 plus 0. So negative 3 plus 0 is negative 3. So far, so good. This is going to be 4 plus 0, which is also just 4. So far, so good still. Negative 3 times 0 is 0. This is just 2. 0 plus 2 is 2. And then we have 4 times 0 is 0, plus 5. So this is 5. So we have proved it. Okay? And if we also go back one more step, we should see that if we're multiplying these two guys, well, A was 2 by 2. Identity was also 2 by 2. So those were the same. And that means that these two are the outer dimensions of my new matrix here, which is still going to be a 2 by 2. Okay? All right, let's go ahead and move on to the last example. And this one has to do with something called vectors. I'm not going to go too much into the vector part because that's a little bit of a different topic. But I did want to show at least a few of them, just in case we have one. Okay, because this is one of those applications where you do see matrices. It's a note up here at the top. A vector, usually written like this, kind of like it looks like a little sideways. Well, it looks like an inequality symbol almost, but it's like a sideways V. This is the same as the matrix column AB. So we can rewrite this as a matrix, as a tiny matrix, if we put it vertically like this, okay? So let V, one of the vectors, be equal to 3, 6, and U equal to 8, 5. Okay, we're gonna use matrices to find each vector. So in the first part, we have V plus U. And I have a little picture here. This is the only one I'm gonna do a picture for, just so you can kind of see how it works with with the application here. And I'm going to add V plus U. So let's go ahead and rewrite V. V is 3, 6. I'm going to write it as a matrix instead. So 3, 6. And then U is 8, 5. Okay. So what I'm going to do is I'm going to add these two guys. So we have 3, 6 plus 8, 5. And remember, this goes back to the previous, the first part of this subunit, where we just add basically the same positions together. So 3 plus 8 is 11, 6 plus 5 is 11. So this is going to be my resulting answer. If we were to write it back in vector form, V plus U would be equal to 11, 11. Okay. Now, how does that apply to this graph that I did up here? Well, let me show you. And again, this is the only one I'm going to show you with like this, just to kind of give you a little bit of an idea how this works. So the vector V was 3, 6. So we can see that we went over 3 to the right and then 6 up. And that's my resultant vector here. Since I'm adding 8, 5 to this, you would go 8 over, so 3 plus 8 is 11, right? So you're kind of thinking something like this. And then you're also going to go up by 5. So we're going to go up by 5. So it lands up here at 11. So we have another vector here. And this represents my U, okay? So 8, 5, kind of like a right triangle. And my resultant vector is V plus U. So this distance here, so the kind of like the line that's made from these two guys, this would be V plus U, this resultant vector here. And that's kind of how this works when you apply it to that. Okay, but if you don't understand, that's okay. That's just a quick FYI. Okay. Let's go ahead and do one more. Or actually, let's skip this one. We're gonna jump over to the multiplication one because I kind of want to do that one. So don't worry about letter B. Don't even worry about it. It's the same deal. Example 11, it says find the product AV if A is this guy and v is 3, 1, and describe the transformations. So we're going to go ahead and rewrite this one as a matrix. So 3, 1, okay? And we're just going to multiply because that's what it's asking us to do here. So AV will be negative 1, 0, 0, 1 times this guy. So times 3, 1. So let's go ahead and do our matrix multiplication here. We have, well, actually, before we do that, this is a 2 by 2, and this is a 2 by 1. So that means that my answer should be the outer ones. It should be a 2 by 1. Okay, so it should be 2 columns. I'm sorry, 2 rows. I always say it backwards. 2 rows, 1 column. We're going to do this kind of sort of in our head. Maybe we can do that. And if you, well, I mean, I can write the steps on here if you want. So for the first one, we're going to have this times this. Negative 1 times 3 plus 0 times 1. Okay, think of it that way. We'll do it like that. Then we're going to have for the second entry, row 2, column 1, it would be row 2, column 1. So 0 times 3 plus 1 times 1. And then we just reduce these. Negative 1 times 3 is negative 3, plus this is going to give me negative 3 still. The second one, 0 times 3 is 0, 1 times 1 is 1. So this is my answer. And if we wanted to graph these, because we're asking for them to describe the transformations, okay? Well, the original V was 3, 1, so 1, 2, 3, 1. This was V, okay? And then AV is negative 3, 1, so negative 3, 2, 3, 1. So this one right here would be our AV. Okay, so it looks like, and my graph's a little bit off, it looks like the transformation that I did is I flipped over the y-axis. So if I wanted to describe this, I could say that this was a reflection over the y-axis. Okay, you might have maybe one problem like this in your homework, so don't worry too much about it if this part doesn't make sense. This is what I want you to focus on, okay? And that's basically it, guys. That's it for 8.2. If you have any questions, always let me know.